Okay, let's unpack this. Have you ever paused to truly think about the incredible, often unseen force that lifts a massive excavator arm with ease? Or, precisely steers a giant tractor across a field? Or even helps an airplane soar and land safely?
Hmm.
More often than not, it's thanks to something called oil hydraulics, a hidden powerhouse that's everywhere around us, even if we don't always see the fluid flowing. This is the deep dive, and today we're taking a shortcut to being well-informed about a stack of fascinating sources that reveal the intricate, powerful world of oil hydraulics. Our mission for you, our listener, is to extract the most important nuggets of knowledge and insight, to give you those genuine aha moments without overwhelming you with information overload. We really want you to walk away with a deep appreciation for this remarkable technology.
And what's truly fascinating here is how oil hydraulics has transformed. It's not just a single component or principle, you see. It's evolved into what our sources call a significant technical cross-sectional discipline.
Cross-sectional. What does that mean exactly?
Well, it means its fundamental principles and diverse applications now span across an astonishing number of engineering fields. Just think about mobile working machines, like excavators, immense wheel loaders, powerful road rollers, and versatile forklifts. They actually convert their entire engine power hydrostatically.
Their entire engine power. Wow.
Yes. And this technology stretches far beyond that, seamlessly integrating with mechanical and electrical systems in everything from our cars to sophisticated machine tools, from critical aircraft systems to vast stationary industrial plants. It's a truly pervasive force.
It's almost startling how foundational it is once you start looking. And the developments have only made it more indispensable. Our sources really underscore that the integration of electronic control and regulation has only made hydraulics even more valuable and precise, right?
Absolutely. It's elevated its role to be a cornerstone of modern mechatronic systems.
Here's where it gets really interesting for me. This isn't some brand new invention, something concocted in a modern lab. The concept of fluid power has roots that stretch deep into history. So how far back does this idea actually go? What's its ancient lineage?
That's a great question. If we connect this to the bigger picture, the very principles of hydraulics, in a, let's say, rudimentary form, stretch way back to antiquity. Imagine we see early examples of ingenuity like Ctesibios from the 3rd century BC. He was a Greek inventor.
Ctesibios.
And he designed what we can visualize as a very early piston pump with 2 opposing cylinders. Quite ingenious for its time, actually. It would draw water through inlet valves and then deliver it under pressure via outlet valves into a central pressure vessel.
A marvel of ancient engineering, really.
It was. However, for many centuries, despite these early glimpses, pressure water hydraulics remained relatively minor in its widespread impact and application. It was more of a curiosity, perhaps.
But then there must have been a turning point, maybe around the 16th century, right? What was the catalyst that truly sparked its growth and evolution?
Exactly. That period was pivotal. We witnessed a significant surge in pressure water pump systems, particularly for what were known as the elaborate Wasserkünste, or water arts.
Water arts, like fancy fountains.
Precisely. Those incredibly intricate, often whimsical water features and fountains popular in the grand gardens and palaces of Europe. It was during this era that many crucial pump designs emerged. For instance, an Italian engineer named Romelli in 1588 described what he called a Kapselkunst.
Kapselkunst.
Yeah, and if you were to see a depiction of it, you'd immediately recognize it as a clear precursor to the vane pumps that are so widely used in oil hydraulics today.
No kidding. So the roots are that direct.
Oh, yes. And remarkably, in that very same book, he also detailed a pump featuring multiple axially moving pistons, which we can directly trace as an early predecessor to our powerful modern axial piston pumps.
Axial piston pumps.
These early designs were often driven by large water wheels and complex angular gears, showcasing a fascinating blend of rudimentary mechanical and fluid power principles working together. It was truly a period of practical invention.
And here's where it gets truly surprising, at least for me. Among these early pioneers, we find perhaps the most unexpected inventor in this space, Johannes Kepler, the astronomer, the man famous for describing planetary motion. How on earth did he fit into the emerging world of fluid dynamics and pump design?
That's a fantastic question, and it really highlights how interconnected scientific inquiry can be. It's absolutely true. The fundamental principle behind the widely used gear pump was actually conceived by Johannes Kepler around 1604.
An astronomer designing pumps.
Right. A man deeply engaged with the cosmos, yet he also had a brilliant grasp of mechanical principles. What's even more remarkable is that he specifically noted that his design required no valves, a significant innovation for the time, simplifying the mechanism greatly.
No valves. Interesting. How did he describe it?
He described it vividly, imagining two or more shafts in an enclosed casing, which intermesh, and each having 6 or more hollow channels, along with 6 round ledges around the circumference, so that the shafts, when rotating, hold water with or without lining, and one empties the other. It's quite descriptive.
It really is.
This ingenious concept later became famously known as the Machina Pappenheimiana. It demonstrates how foundational scientific minds, often from seemingly unrelated fields, were laying the essential groundwork.
So what does this centuries-long development mean for modern hydraulics? After all this initial innovation, when did oil hydraulics really take off and become the omnipresent powerhouse we recognize today?
The real boom, the moment it transformed from, let's say, a niche technology to a cornerstone of industry, happened much later, predominantly after the Second World War. This period led to its widespread adoption across virtually all areas of mechanical engineering.
Okay, post-WWII.
Yes. Our sources vividly highlight a particularly spectacular and rapid technological shift: the replacement of traditional cable excavators by their far more efficient hydraulic counterparts.
Ah, yes, the shift from cables to hydraulics in excavators. That was huge.
It was enormous. This change was notably spearheaded by companies like DMAG in 1954, and the economic impact was, and continues to be, immense, truly transforming entire industries.
Can you give us a sense of that scale?
Absolutely. To give you an idea, the annual turnover for hydraulic companies represented by the VDMA, the German Engineering Federation, it just soared from a modest 0.4 billion Deutschmarks in 1966 to a staggering 2.2 billion Deutschmarks by 1981.
Wow, that's a huge jump in just 15 years.
Massive. And by 2018, that figure had ballooned to an astounding 5.4 billion euros. That's not just a number. That lip reflects how deeply interwoven hydraulics became with industrial progress. It propelled Germany into a decades-long lead in global exports.
So massive economic impact.
Immense. It speaks to the relentless innovation that transformed this technology. This success was so profound, it was publicly recognized in 1997. Honoring Professor Wolfgang Back for his groundbreaking research contributions, and manager Werner Dieter for his pivotal role in industry, acknowledging both science and industry.
Right, recognizing both sides of the coin. Okay, let's transition from that rich history to the absolute heart of any hydraulic system. The fluid itself is clearly more than just a liquid you pour in, isn't it? What are its primary roles, and why is it so incredibly specialized?
You're absolutely right. It's the lifeblood of the system. The industry uses a very specific term for them: Druckflüssigkeiten, or pressure fluids.
Pressure fluids, okay.
This emphasizes their primary and most crucial tasks: energy and signal transmission within the hydraulic system. They are the medium through which force and movement are translated, but their importance doesn't stop there. They also have a suite of crucial secondary roles that are just as vital for the system's long-term health and performance. Well, lubricating all the moving parts, significantly reducing wear, providing essential corrosion protection, damping unwanted vibrations, dissipating the considerable heat generated, and even cleaning and carrying away microscopic contaminants. It's truly a multifunctional, highly engineered component.
So, given all those demanding roles, what are the key properties and challenges that define a truly effective hydraulic fluid? What makes a fluid good in this context?
The requirements are incredibly specific and can vary greatly depending on the particular system and its operating conditions. Take viscosity, for instance.
Viscosity, right? The thickness.
Exactly. A high viscosity is beneficial because it provides better lubrication and helps reduce leakage losses, which is generally good for efficiency. However, on the flip side, too high a viscosity also increases shear and flow losses within the system, potentially impacting overall efficiency. It's a classic engineering trade-off.
Finding that sweet spot.
Precisely. Other vital requirements include robust corrosion protection, complete compatibility with various sealing materials like rubber and plastics, and critically high aging resistance. This is especially important under the high operating temperatures typical of hydraulic systems.
Why is aging resistance so crucial?
Because the fluid must resist oxidation, which leads to harmful acid formation, and polymerization, which results in that dreaded sludge and resin formation. Both can severely damage delicate components.
Sludge and resin. Yeah, definitely bad news.
And perhaps most uniquely, the fluid must exhibit extremely favorable behavior towards air. It needs good air release so bubbles don't linger, a low tendency to foam, and sufficient air solubility.
It sounds like a complex chemical dance.
Yeah.
I imagine there are different flavors or categories of these fluids, each designed for specific uses or environments. What are the main types?
Indeed, there's a specific fluid for nearly every application. The most common type, by far, are mineral oil-based pressure fluids. An excellent example is HLP46, which is incredibly prevalent, especially here in Europe. These aren't just raw mineral oils, though. They are specially blended with a precise cocktail of additives to significantly improve critical properties like viscosity, temperature behavior, wear protection, and aging resistance.
Okay, so enhanced mineral oils. What else?
Then we have fire-resistant fluids. These are absolutely crucial for environments where there's a high risk of fire or explosion, like in mining or steelworks. These fluids are ingeniously engineered with much higher ignition temperatures, or in some cases are designed to be entirely non-flammable.
Makes sense for those environments. What types are there?
This category includes water-containing types, designated HFA, HFB, and HFC, and completely water-free synthetic fluids known as HFD.
Right. And you mentioned biodegradability earlier.
Yes, finally, and increasingly important for environmental reasons, are the rapidly biodegradable pressure fluids. These are often based on renewable resources, like plant oils, such as rapeseed oil, classified as HETG, or on synthetic esters, known as HEES.
Biodegradable sounds like a fantastic step forward for environmental protection. But is it ever a case of too good to be true? Are there any downsides or specific considerations engineers need to keep in mind? Seems like there might be a trade-off.
That's a really important question, and you've hit on a critical point. Well, rapeseed oil, for instance, is a wonderful renewable resource and offers excellent lubrication and corrosion protection. It does come with specific engineering challenges. For one, its viscosity tends to increase quite significantly below Manila 5 degrees C.
So cold weather performance could be an issue.
Potentially, yes. And at high temperatures, specifically above 70 degrees C, its oxidative stability can become critical, possibly leading to gumming or varnish formation.
Gumming, yeah, not good.
But perhaps the most difficult challenge to manage with bio-oils is their tendency towards hydrolysis, essentially, a chemical reaction also known as saponification, if water gets into the system.
Hydrolysis, saponification. So water contamination is a big problem.
It can be. This property, ironically, is precisely what supports its biodegradability in the environment. So to prevent issues within the hydraulic system itself, very strict measures often need to be taken to keep water content extremely low, typically below 100 parts per million.
100 ppm, that's incredibly low.
It is. It's a testament to the fact that seemingly simple material choices have complex system-wide effects. And just for context, even standard mineral oil is biodegradable, just much, much slower.
Right, good point. Okay, now we've got a handle on the fluid itself. Let's get into the nitty-gritty. How do these fluids actually generate force and movement? What are the fundamental physical principles at play that allow a small input to create such immense power?
At its very core, it's all about physics, specifically the principles of hydrostatics and hydrodynamics.
Hydrostatics and hydrodynamics.
Okay, let's start with hydrostatics, which deals with fluids at rest. Here, the concept is quite simple. Pressure is fundamentally just force distributed over an area, or P equal FA. This pressure acts uniformly and perpendicularly within a contained fluid, pushing out equally in all directions.
Pascal's principle, right?
Exactly. In most oil hydraulic calculations, the fluid's own weight is actually so negligible compared to the working pressure that we can effectively ignore it, simplifying things. This fundamental principle allows for truly significant force amplification, like in a hydraulic jack. A small force on a small piston creates an incredibly large force on a much larger piston area.
Like magic, but physics.
Precisely. But there's a direct trade-off. If the force is amplified by 10, the speed of the large piston is proportionally reduced by 10. You gain force, but you exchange speed.
So a powerful but slow push. What happens when the fluid starts moving? That brings us to hydrodynamics, I assume.
Exactly. When the fluid is in motion, we bring in the principles of hydrodynamics. One of the first concepts is the continuity equation. This is elegantly simple. For an incompressible fluid, and oil is largely considered incompressible for these purposes, the volume flow rate must remain constant throughout a pipe.
Okay, constant flow rate.
So what that means in practice is if the pipe's area decreases, the fluid's velocity must increase to maintain that constant flow. A1V1 equaled A2V2.
Like putting your thumb over a garden hose to make the water spray faster.
Exactly that principle. You decrease the area, velocity increases. Building on that, we have Bernoulli's equation. This foundational principle states that the total energy content of an ideal, frictionless, steadily flowing fluid remains constant along a streamline.
Total energy. Pressure, velocity, height.
Correct. This equation is incredibly powerful for understanding the relationship between pressure, velocity, and height in a flowing system. It's key for analyzing energy conservation.
That makes sense. But in real-world systems, nothing is truly ideal or frictionless, right? So what about pressure losses? How do engineers account for those?
You've hit on a critical real-world factor: pressure losses. Friction is inevitable, causing energy dissipation that manifests as pressure loss. This is absolutely vital for designing efficient systems. In pipes, whether the flow is smooth and orderly laminar flow below Reynolds number 2000 or chaotic and swirling turbulent flow, at higher Reynolds numbers fundamentally changes how losses behave.
How so?
For laminar flow, pressure drop is simply linearly proportional to the flow rate. But for turbulent flow, it gets more complex. Pressure drop is approximately proportional to the square of the flow rate.
Square of the flow rate, so losses increase much faster in turbulent flow.
Much faster. Our sources point out operating points often fall in that tricky transition region. For instance, a 17-millimeter pipe with 6-meter flow of HLP 46 oil at 60 degrees C has a Reynolds number of 4,000 right in that zone. Beyond pipe friction, we also account for local losses from bends, branches, sudden diameter changes.
Well, the fittings and turns.
Exactly. Another critical area is flow in throttles and gaps. These act as functional hydraulic resistances, intentionally controlling flow. We have laminar resistances, like tiny capillaries designed with small diameters for laminar conditions, and turbulent resistances, like orifices, which are less affected by viscosity changes.
And what about leaks? Even in a seemingly sealed system, it seems like leakage would be a big deal.
It's a huge deal. A very significant consideration, often a major source of inefficiency, is leakage flow. These tiny leakage currents occur in the incredibly precise, pressurized gaps between functional surfaces in pumps, motors, valves.
Those tiny gaps.
Yes. While they offer some minor lubrication and cooling, they primarily reduce efficiency and affect control quality. A crucial, almost counterintuitive point highlighted is that leakage flow increases with the third power of the gap width.
The third power, so a tiny bit more wear, makes a huge difference in leakage.
A disproportionately large difference. For example, if the inner part is slightly eccentrically positioned, leakage can increase by up to 2.5 times. It emphasizes the extreme precision needed.
Wow. Microscopic tolerances, macroscopic impacts.
Absolutely. Finally, we consider the force effects of flowing fluids via the impulse theorem. This is about what happens when the fluid's speed or direction changes. Mass forces are exerted on guiding elements.
Like forces on valve spools or in bends.
Exactly. All vital for design.
Speaking of preventing wear and ensuring components last, I've heard about supporting oil films. What exactly are those, and why are they so incredibly important?
That leads us to a really interesting and vital concept. In oil hydraulics, plain bearings aren't just for traditional rotating shafts. They show up in many subtle forms. Think about pistons and cylinders of axial piston machines, rotating cylinder blocks against fixed control plates, slippo pads on swash plates, vanes in vane machines.
Okay, so lots of sliding contacts under high load.
Precisely. These contacts are often highly loaded, operating under immense pressures where metal-on-metal contact would be disastrous. Therefore, a separating load-carrying oil film is structurally essential to prevent direct contact and wear. It's like a cushion of oil components float on.
A hydrodynamic cushion.
Yes. Engineers use tools like the Sommerfeld number to characterize the operating regime, predicting if components are gliding smoothly on a full oil cushion or in mixed friction or worse. The goal is always full fluid lubrication for optimal durability. It ensures metal surfaces are constantly separated by that vital, protective film of oil.
Incredible precision. Now that we have a solid understanding of the fluid and the physics, how do engineers actually direct and control this immense power? I imagine valves play an absolutely central role.
They are, without a doubt, the conductors of the hydraulic orchestra. Valves are the core devices for energy control and regulation. Our sources clearly highlight that they are the traffic cops, determining flow direction, regulating flow rates, and limiting pressures to ensure the system operates exactly as intended.
And they fall into categories.
Yes. Systematically classified into directional control valves, pressure control valves, flow control valves, and shutoff valves, each with a distinct purpose, a very logical system.
And how are these valves actually actuated or moved? I know there's a strong trend towards electronic control, moving away from older levers. What's driving that?
Indeed, the shift towards electronic actuation is profound. While manual, hydraulic, and pneumatic actuations still exist, the trend is overwhelmingly towards electrical control. This often involves sophisticated components like proportional magnets. These aren't just on-off, they're designed so their force or displacement is directly proportional to an input electrical signal, usually current.
Proportional control.
Exactly, allowing single-stage generation of flow or pressure proportional to the signal, offering incredibly fine control. A very common technique is pulse width modulation, PWM, which modulates the current and cleverly helps reduce spool friction.
Reducing friction too, that's smart.
It is. And more recently, for demanding applications like diesel injection valves, piezo actuators have emerged. They generate huge forces but tiny displacements, so they need mechanical or hydrostatic displacement amplifiers for hydraulic valves.
Let's delve into a specific and very common type. Directional control valves, or Ventil. What are their different forms and behaviors?
Directional control valves are fundamental, broadly categorized into spool valves, Längsschieber, and seat valves, Sitzventil. Each has distinct characteristics.
Okay, spool versus seat. Let's start with seat valves.
Right, seat valves. Their significant main advantage is they close incredibly tightly, ensuring a near-perfect seal. Ideal for holding loads precisely, like on lifting platforms. They're also generally less sensitive to contamination and wear. Robust.
But there are downsides.
Trade-offs, yes. They tend to be more expensive, harder to pilot with fine adjustments, may be prone to vibration, and typically require greater actuation forces.
Okay. And spool valves.
Spool valves are incredibly common due to versatility and dynamic capabilities. A critical design parameter here is overlap.
Overlap.
Positive overlap means the spool end completely covers the port in neutral, ensuring good sealing between chambers of different pressures, minimizing leakage when closed. For precise control and fine metering, engineers often machine small, almost microscopic axial notches or grooves into the spool ends.
Notches for fine control.
Exactly, allowing tiny flows before the full cross-section opens. Then there's null overlap, where the land exactly matches the port. This gives linear characteristics beneficial for throttling valves and fast control loops, often in servo valves.
And negative overlap.
Negative overlap is sometimes used for highly throttling directional valves in high dynamic actuators, allowing very rapid responses.
You mentioned spool clearance is tiny.
Incredibly small, typically 0.2 to 0.5 per thousand, much smaller than plain bearings. This extreme precision is necessary because leakage increases with the third power of the gap width.
That third power law again.
It dictates everything. And managing actuation forces is also a challenge. Static forces can usually be balanced, but friction and axial flow forces are tricky. Clever designs and even intentionally induced vibrations, a dither signal, can reduce friction, ensuring smooth spool movement.
A dither signal, like shaking it slightly.
Essentially, yes. High-frequency, low-amplitude vibration to overcome stiction.
You mentioned servo valves earlier and their remarkable amplification. Can you elaborate on how they work to achieve such precise control? It sounds almost like magic.
What's truly fascinating is how servo valves, often multi-stage, achieve truly remarkable amplification. A mere 0.2 watt electrical input can control a massive 20 kilowatts of hydraulic power.
0.2 W controlling 20 kilowatts. That's huge amplification.
Enormous. A classic servo valve often uses a nozzle flapper amplifier in its first stage. Imagine a tiny flapper positioned precisely between two nozzles flowing oil. A small electromechanical transducer, a torque motor, moves the flapper subtly. This changes the back pressure in the two lines from the nozzles.
Okay, changing back pressure.
This creates a pressure difference, which then acts on the main spool, shifting it. The first stage functions like a sophisticated Wheatstone half-bridge, converting a tiny electrical signal into a powerful hydraulic pressure signal.
So it's a multi-stage process.
Often, yes. Because of their extreme precision and tiny tolerances, they require exceptionally fine filtration and often a small, continuous flow even at rest for optimal performance. Marvels of miniaturized power control.
So what's the big difference between just controlling something and regulating it in hydraulics? Seems subtle but important.
That's a great question, and it gets to the heart of mechatronics, that blend of mechanics, hydraulics, electrics, electronics. Both control and regulation aim to bring a system's output to a desired value. The key difference, however, lies in feedback.
Feedback, okay.
Let's look at control, or Steuerung. This is an open-loop system. The output is set by the input, but critically, there's no measurement of the actual output fed back to correct for disturbances.
Like setting a thermostat without it checking the room temp.
Exactly. You said it in hope. Regulation, or Regelung, however, is a much smarter closed-loop system. Here, the actual output, the actual value, or Istwert, is constantly measured by a sensor. This measurement is continuously fed back to a controller.
Measuring the output.
Yes. The controller compares this Istwert to your desired input, the set point or solvert. If there's a difference, the controller generates a corrective signal to the actuator. This constant feedback loop means the system is always adjusting, always striving to maintain the desired output, making regulation far more precise, robust, and adaptive.
So regulation is definitely smarter because it self-corrects.
Yeah.
What are the unique advantages hydraulics brings to these control and regulation systems, especially compared to purely electrical alternatives? Where does it still outperform?
Despite rapid advances elsewhere, hydraulics truly excels in specific areas where its inherent strengths shine. Firstly, unparalleled ability to generate very large forces or torques in a remarkably small space. High power density.
Huge power in a small package.
Exactly, a massive advantage where space weights are premium. Additionally, hydraulic actuators typically have small masses and low rotational inertias, contributing to exceptional agility and responsiveness. And they provide very large analog amplification factors. Small input controls large output precisely.
So power density, low inertia, high amplification.
These characteristics lead to incredibly high dynamics in actuators, meaning fast mechatronic systems responding quickly, powerfully, precisely. To optimize these complex systems, engineers heavily rely on computer-aided simulations. MATLAB Simulink for system behavior, CFD for detailed flow analysis.
Using simulation to tune everything.
Essential now, and information exchange between subsystems often uses BUS systems, not just saving wiring, but allowing sensor signals for multiple uses. Data documentation, operational management, remote diagnostics.
Making the whole system smarter and more connected.
Precisely. It's a highly integrated, intelligent approach.
That makes sense. Building on individual components, how are these hydraulic blocks actually combined and configured to create functional systems that do real work, like moving an excavator arm? What are the fundamental ways they're linked?
At the system level, we often start with basic circuit diagrams, the blueprints. Two fundamental ways to connect consumers, like motors or cylinders, are in parallel or in series.
Parallel versus series, okay.
Let's consider a parallel connection first. Both consumers get the same pressure. However, the flow splits between them. Critically, in simple parallel circuits, typically only the consumer with the lowest load pressure, least resistance will actually move. The other might stay stationary.
Ah, so the path of least resistance takes all the flow.
Essentially, yes. This behavior is usually unacceptable for simultaneous movement, so engineers add flow control or flow divider valves to manage it.
Okay, so parallel needs extra control. What about series?
A series connection works differently. Flow through both consumers is essentially equal, ignoring tiny leakages. The pressures, however, add up depending on individual loads. This arrangement is excellent for achieving precise synchronization, especially with hydraulic cylinders, which are usually very tight. Highly predictable, coordinated movement.
Great for synchronization, then.
Yeah.
You mentioned load sensing earlier as an energy-saving concept. Can you deep dive into that? Why is it such a significant innovation?
Load sensing, especially with a variable displacement pump, is indeed a cornerstone innovation for energy efficiency. The core idea is brilliantly simple, yet impactful. Move away from older, constant flow systems.
Those older systems waste energy, right? Pumping full flow even when it's not needed.
Exactly. Huge energy waste through throttling and heat. The load sensing principle ensures the pump delivers only the precise flow and pressure the system actually needs at any given moment. It's on demand. This dramatically reduces throttling losses. How? It involves continuously measuring the load pressure at the consumers, sensing how much resistance the cylinder or motor faces.
So it knows the actual load.
Precisely. This load pressure signal is fed back to the variable pump, which instantly adjusts its displacement, its output volume, to exactly match demand. A dynamic, closed-loop system adapting in real time.
Very clever. When did this catch on?
First commercialized in tractors by Alice Chalmers in '73, but it truly gained widespread adoption after '87 with Case IH tractors, supported by significant research, particularly in Germany. Today, modern load sensing systems are increasingly mechatronic, integrating advanced pressure sensors and electrohydraulic valves for even greater precision and efficiency. Smart engineering meeting environmental goals.
A crucial practical consideration in any powerful hydraulic system must be heat. Why is heat management so incredibly important, and what happens if it's not properly addressed? Seems like a silent killer.
You've hit on one of the most fundamental challenges. All energy losses within a hydraulic system ultimately manifest as heat. Thermodynamic certainty. If not managed, rising oil temperatures lead to a cascade of negative effects. Accelerated oil aging, diminished lubrication effectiveness, damage to seals and other components.
Leading to leaks and failures.
Exactly. The target operating temperature is typically between 50 and 80 degrees C.
How does heat escape naturally?
Through the surfaces of the oil tank and piping. However, for most larger systems, this passive dissipation is insufficient. There's a fundamental geometric reality. Power and losses scale roughly with the cube of size, while heat dissipating surface area only scales with the square.
Ah, so bigger systems generate proportionally more heat than they can naturally shed.
Correct. Small systems might not need a cooler, but larger ones almost invariably do.
So coolers are essential. What types are common?
Specialized components called coolers, or Wärmetauscher. Common types include oil-air coolers, like car radiators, used mainly in mobile hydraulics or where cold water isn't available. Oil-water coolers are more common in stationary applications, offering high cooling capacities. They typically use an efficient counterflow principle, maximizing temperature difference for efficient heat transfer.
And managing heat impacts the bottom line too, I assume.
Directly. High losses mean expensive coolers, larger pumps, higher operating costs, energy consumption, and higher costs for the cooling medium. Managing heat is about performance and profitability.
Beyond efficiency and longevity, another aspect often overlooked is noise. Hydraulic systems can be quite noisy. How is noise generated, and what strategies do engineers use to tackle it? Important for operators.
The field of acoustics is indeed critical here, especially occupationally. High continuous noise, above 90 dBA, can cause irreversible hearing damage.
How does the noise actually happen?
It follows a typical noise chain. Starts with rapid oil pressure fluctuations, dPdt. These create cyclic force fluctuations, dFdt, on components. These forces transmit as structure-borne noise, Körperschall, vibrating through the machine's material. Finally, these vibrations excite surfaces, like housings, radiating airborne noise, Luftschall, which we hear.
Pressure changes to force changes to structural vibration to airborne sound.
That's the chain. Engineers work to reduce noise at multiple points. For example, Bosch's Silence Plus gear pump uses a non-involute tooth profile, astonishingly resembling Kepler's original idea. This allows drastically reduced noise levels up to 15 dBA less. A significant improvement.
Wow, going back to Kepler for quiet pumps, what about other measures?
Beyond component design, secondary measures fall into 4 groups. Structure-borne sound insulation, elastic mounts for pumps like shock absorbers, structure-borne sound damping, materials absorbing vibrations, airborne sound insulation, sealed enclosures around noisy parts, and airborne sound damping, sound-absorbing linings inside enclosures.
A multi-pronged approach. Does it work?
Yes. Fourier analysis helps identify specific noise frequencies. For example, a research tractor achieved an 11 dBA reduction at the driver's ear using such measures. Makes a huge difference. Clever designs integrate noise reduction too, like U-shaped oil tanks around motor pump units providing natural sound insulation. Holistic design helps.
So we've covered components, physics, design challenges. Now let's bring it all together. Let's see these principles in action with some real-world examples that showcase the power and versatility.
One of the most significant applications is in hydrostatic transmissions, widely used in stationary and mobile machines, from small forklifts to massive construction equipment, transmitting power using fluid.
And there are different types.
2 main types: direct hydrostatic transmissions, transmitting all power hydraulically, and power split hydrostatic transmissions, dividing power between hydraulic and mechanical paths. This split often leads to higher overall efficiency.
Better efficiency, that's key. What are the advantages over mechanical gearboxes? Numerous. Stepless speed variation, infinitely adjustable speeds, super smooth. Fine and almost load-independent control speed stays consistent regardless of load. Simple, starting without a clutch. Easy directional reversal, and effective braking by using the hydraulic motor as a pump to absorb energy.
Very versatile. Any examples?
An early hydrostatic compact transmission was used in International Harvester (IHC) tractors from 67 to 84, estimated 15,000 units. Pioneering design with pump and motor in a space-saving back-to-back configuration. More recently, the Leibherr 2+2 drive for wheel loaders, developed with Bosch Rexroth and Dana Spicer since 2002, uses a variable swash plate pump with 2 variable bent axis motors.
2+2. What does that achieve?
This modular design allows 3 stepless speed ranges and significantly improves fuel efficiency, claiming up to 20% less fuel consumption compared to traditional hydrodynamic converters. Huge operational saving.
That 20% fuel savings is truly impressive, and it naturally brings us to a major theme: energy efficiency and climate protection. How is hydraulics contributing to this critical global effort? Climate protection is indeed a major driving force. Leading manufacturers identify 4 key areas for energy-saving concepts: using low-loss components, implementing on-demand flow to avoid throttling, incorporating energy recuperation, and utilizing system simulation for optimization.
Tackling those inherent losses, throttling idle losses.
Exactly. The weaknesses often lie there, not in the displacement units themselves. Intelligent systems minimize these. A significant advancement is electrohydraulics, combining variable speed electric motors with displacement machines, allows demand-oriented oil flows, leading to substantial energy savings.
And energy recuperation.
Yeah.
Capturing wasted energy. That sounds incredibly clever. Can you give us some examples?
Absolutely. This is where hydraulic engineering ingenuity really shines. First, consider refuse collection vehicles. Bosch, Rexroth, and Haller developed a system where braking energy is captured by an axial piston unit acting as a pump, storing energy in accumulators.
Storing braking energy.
Yes, this stored energy is then released by the unit acting as a motor to assist acceleration. Achieved about 20% fuel savings and reduced brake wear.
20% savings just from braking. Wow. What else?
Next, massive harbor cranes. Liebherr's Mechatronics system recovers energy when lowering heavy loads. Main pumps act as motors, filling accumulators. This captured energy assists the next lift, allows a smaller, quieter, more consistently loaded primary motor, resulting in about 30% fuel savings. Elegant solution for high power demands.
30% on a harbor crane. Impressive.
Moving to excavators, the Caterpillar 336E from 2013 was one of the first production excavators with hydraulic swing energy recuperation. Braking energy from the swing mechanism is stored in accumulators, then used to assist acceleration, allows a smaller diesel engine, saving fuel, recovering dynamic energy.
Even capturing the energy from swinging. Clever.
Even for less obvious applications like road rollers, hydraulic storage has enabled engine downsizing. An additional pump charges an accumulator during power surplus periods. Power peaks for the vibration drive can then be met by the accumulator. Allowed one model to reduce its engine from 85 kilowatts to 55.4 kilowatts, leading to 15% fuel savings.
Downsizing the engine by using stored hydraulic power.
Finally, in industrial presses. Manufacturers like Lasco and Schuler achieved over 20% energy savings, using purely volumetric control instead of throttling, and recuperating potential energy from lowering the ram and compression energy released after the stroke. Holistic efficiency.
It's incredible to see how these systems become smarter, more integrated, adapting, and becoming more sustainable. Finally, let's briefly touch upon hydraulics in a very high-stakes environment. Aircraft. How does it ensure safety there?
Aircraft hydraulics is the quintessential example of robustness and redundancy pushed to the absolute limits. Take the Tornado fighter jet system. Operates at 270 bar. It's designed with 2 completely independent subsystems, each driven by its own engine-driven variable displacement pump. Ensures full capability even if one engine or system fails.
The great redundancy.
Plus, an electrically driven emergency pump uses a surprisingly small fluid volume, 16.2 liters, and its coolers cleverly preheat the jet fuel, leveraging waste heat.
Ingenious integration. What about damage?
The battle damage control system is fascinating. If a leak reduces fluid volume, a switch automatically isolates most non-essential consumers from the affected side. Ensures vital primary flight control functions remain operational, absolutely critical.
Keeping the essential controls working no matter what.
And for the ultimate fail-safe, if both hydraulics and electrohydraulic controls fail, a mechanical connection can be engaged, allowing the aircraft to remain flyable, albeit with more effort. Incredible safety engineering.
Wow. What an absolutely incredible deep dive. From ancient water pumps and surprising astronomical insights to cutting-edge energy recuperation and critical systems in fighter jets. We've seen just how pervasive, ingenious, and fundamental oil hydraulics truly is. It's a field constantly pushing boundaries, balancing immense power with precision and, increasingly, efficiency.
That's a truly insightful point, and the innovation isn't slowing down. As our sources highlight, future developments are looking at things like relocating oil functions to component surfaces through ceramic materials or special coatings.
Embedding functions onto surfaces.
Exactly. Suggests a continuous evolution towards even more integrated, durable, perhaps smaller systems, where the fluid plays an even more foundational role in surface interactions. Critical thinking is essential, and understanding these principles helps you appreciate the relentless innovation driving these unseen technologies.
So what does this all mean for you? Perhaps next time you see a massive construction vehicle effortlessly moving earth, or even consider the braking system in your car, you'll have a newfound, profound appreciation for the complex yet elegantly simple world of fluid power. It's truly everywhere. What new frontiers do you think the ongoing combination of mechatronics and these advanced materials will unlock? What kind of next-generation machines might this incredible hidden power enable? We'd absolutely love to hear your thoughts. Join us next time on The Deep Dive for another journey into the core of fascinating topics.